Okay, let's now continue again with what we were doing. We had a kind of a truncated class last time because we looked at the midsem, so we didn't make too much progress. But we looked at the so-called periodic Sturm-Liouville problem. And the midsem, you're welcome to ask any questions related to the corrections because I do make mistakes, and you are welcome to seek corrections. Okay, so the initial equation that we start with for this guy is the same as what we always have had, which is f double prime is minus lambda f. And when we talk about a periodic Sturm-Liouville system, we're talking about P of minus L equal to P of L. Remember that Px y y prime plus Qxy was equal to lambda y. So that P is going to be also periodic in some sense. P minus L is equal to P at L. And in this particular case, it is equal to 1, so it hardly matters what is P minus L, PL. The function value at the endpoints are going to be the same. We have taken L and minus L, and the gradient of the function is going to be the same at L and minus L. This is what we have chosen as the representative periodic Sturm-Liouville system. And in all of this, we have said that we would look at lambda equal to 0 to start with, and then look at the other eigenvalues. And in everything that we have done so far, lambda equal to 0 was always a trivial solution. But in this particular case, it turns out it is not. And that's why this example was picked to impress on you that lambda equal to 0 is not always an eigenvalue that you can throw out. So when we used lambda equal to 0, we got the function as equal to some constant b, and so you need to retain it. Then we looked at the next other options, lambda equal to minus k square, which turns into a trivial solution. We didn't do the algebra, we just said that you can look at the algebra there, and it's not guaranteed that all of lambda equal to plus k square or minus k square are going to end up like this, but in this case it is. So we went ahead and said that you can go ahead and look at the algebra that is given there and convince yourself that lambda equal to minus k square is going to end up with the trivial solution. Finally, we considered lambda equal to plus k square, and usually this is the case which is going to give you the eigenvalues because you are having cosines and sines, and these are periodic functions which are going to give you multiple solutions. Okay, so we started by looking at the first condition, FL equal to f of minus L, and that said that B sine KL is going to be equal to 0. And then you look at the next condition, which is f prime L equal to f prime minus L, and that gave you A sine KL equal to 0. And between the two of these expressions, we can say that if you are looking for a non-trivial solution, A and B have to be selected to be non-zero, and sine KL is going to be equal to 0, and you're going to get the eigenvalues from there. Okay, so you get KL equal to n pi, and you're going to get your eigenvalues as n pi by L. Okay, so the solution became that, and what we said was that this is one of the solutions to the equation which we started out with, which is f double prime equal to minus lambda f, and every eigenvalue is going to give you a solution. And because we are talking about a linear system, a sum of the solutions also is going to be a solution, and that is nothing but your Fourier series. Okay? Because you had your sines, you had your cosines, and sum of all of these we said were going to be amenable to give you any function whatsoever in that 2 pi periodic space, or in the space that is going to be dictated by those conditions that we had, in this particular case, the periodic Sturm-Liouville system. And the reason being that Sturm-Liouville system is going to tell you that these eigenfunctions are orthogonal. Okay, and in this particular case, it appears to be straightforward, because we all know from trig functions that the n pi by L are orthogonal, or n pi x by L, sines and cosines are orthogonal to each other when n's are going to be integers. So we'll look at an example just now in 1 minute where this is not going to be holding. So we are very clear that the orthogonality needs to be somehow established from other means, and that's the Sturm-Liouville system. Okay, so that was one example, and here's another example that we saw in the past. This is the Legendre equation, and what we said was that in the past, when we were looking at series solutions, we said that there is an expression or an equation of this nature, which is going to be what is called the Legendre polynomials are going to emerge as the solution to this particular equation. Okay. And if we look at this guy here, this is in the Sturm-Liouville form, because if you recall your Sturm-Liouville form, we said py prime, the whole prime, and then there was a qy, and then there was a lambda y times a w. Okay. So if I look at this first expression here, I can just write this as 1 minus x square y prime, the whole prime, and then this is n plus 1 y equal to 0. So this guy is 1 minus x square y double prime, this guy is 2x y prime, and that's the third term there. So my eigenvalues are these n into n plus 1. Okay. So it is in the Sturm-Liouville form, and in the past we have obtained these solutions to these y values, and these y's are nothing but your eigenfunctions, and that means that the y's which we have obtained, which are these Legendre polynomials, are all orthogonal. Okay, so just by looking at the fact that this guy is conforming to that Sturm-Liouville type of a system, boundary conditions we have not written, but you can write them. So any function you can represent in the form of the summation of these Legendre polynomials. Okay, well, it's a nice concept, but it's pretty painful to use, so nobody uses it. Okay, but in principle, this guy is a Sturm-Liouville form, and when I say nobody uses it for representation of functions that I know of, but I'm not sure if others are there who really use it, but I'm sure the orthogonality is something that people use in various other fields. Okay, but we are not going to be using the Legendre polynomials to represent any polynomials of interest to us. Okay. One more example is the Chebyshev equation, and the Chebyshev equation looks very, very similar to this guy, except that I don't have this guy 2 in there. Okay? Otherwise, the equation is pretty much the same. Okay? So there is an n square here, and once again, this guy is in the Sturm-Liouville form. Okay? So the Sturm-Liouville form is a little bit more messier than this one, but it's fairly straightforward to get. You can go ahead and get it. So you get minus of 1 over, no, so this is square root. So if we are looking at the Chebyshev equation, it is square root of 1 minus x square y prime the whole prime, right? And then you can show that you have n square is equal to n square 1 by under root 1 minus x square y. Okay. The reason I'm showing you this as an example is because now this is my p of x and this guy is my w. Okay. So in this particular example, my w is not equal to 1 anymore. The rest of the algebra is not required. The only thing that we need to appreciate in this slide is the fact that the top guy, which is the Chebyshev equation, is in the Sturm-Liouville form, which is this guy here. So this is in the Sturm-Liouville form where P happens to be equal to 1 minus x square under root, and the W is also there, which is 1 by under root 1 minus x square. And the inner product now, the inner product is no longer just the inner product of two functions. Remember we said was the inner product of two functions in this framework we said was equal to f and then g, and then there is a w. In the past, so far, wherever we have seen the Sturm-Liouville system, the w has been equal to 1. Okay, it no longer is 1 here. Okay, that's all I want to impress on in this particular slide. So there are several other examples of these so-called polynomials which are going to be in this so-called Sturm-Liouville form, and they are all orthogonal to each other, and the orthogonality is going to be useful to you in maybe various places, but for this particular course we are not going to be using the orthogonality of these polynomials explicitly per se. Okay. All right, so one last example. Okay, so there are several other functions, the Hermite, the Bessel, all these guys exhibit orthogonality, these functions, and you are going to be able to show that they are orthogonal largely based on the fact that they are going to be amenable to this Sturm-Liouville system form. Okay. But of course, sines and cosines are the most popular, which is the Fourier series that we saw, and it's only sometimes that the other functions are going to become useful to us. Okay. All right. What is more useful to us is the fact that sometimes, not these complex guys, but there are going to be situations where we are going to do separation of variables and you are going to be ending up in not just f double prime equal to lambda f type of equation, but some other types of equations. So we'll look at one example and then we'll say that we know how to deal with this Sturm-Liouville system. Okay. All right, so let's take this example. Y double prime plus Y prime plus lambda Y equal to 0. And you have got Y0 equal to 0 and Y2 equal to 0. In the past, in one of the earlier classes, we have seen there is a formal methodology to go ahead and convert any equation of this form into the Sturm-Liouville form. In this particular case, it is fairly easy. You just say y prime e to the x prime and plus lambda e to the x y is going to be equal to 0. Okay, so that's going to be the form which is going to be what you're going to get when you're going to process that second order differential equation and try to put it into the Sturm-Liouville system form. So this is this form, and now you see that we have a situation where this guy is W, this is W of x, and this guy is my P of x. So I've got a P of x which is non-unity and a W of x which is non-unity. Q is 0 because the second term in the Sturm-Liouville system that we had is equal to 0. Okay. All right, let's try to get the solution. We'll come back to this in 1 minute, but let us try to get the solution for this equation. How do you get the solution to this equation? What is the solution to this? How do you solve that differential equation? This guy here. This is something that we did. Y equal to e to the mx or e to the lambda x. You assume that the solution is going to be looking something like that, and then brute force plug it in and see what happens. Okay, we brute force plug it in, and you are going to get m square plus m plus lambda equal to 0. Okay, so this is the equation that we need to solve to get what the m's are. And if you go ahead and solve this guy, you're going to get m is minus 1 plus minus root under 1 minus 4 lambda by 2. So this is going to be the solution to that. And now what are the different cases now? What are the different cases for this? Because lambda is a floating number now. What could be the different cases? Oscillation. Anything else? Damped or not, we'll worry about later. One is an oscillatory solution. Then one could be an exponential solution. One could be equal roots. So all the possibilities are there, right? So if, and of course, the most ubiquitous one is lambda equal to 0 is also a possibility, right? So lambda equal to 0 is a possibility, and then you have got 1 minus 4 lambda greater than 0 is a possibility, 1 minus 4 lambda equal to 0 is a possibility, 1 minus 4 lambda less than 0 is a possibility. Okay. So which one is going to be my oscillatory solution? This one here. Okay. So again, I'm not going to go through the algebra for all these cases. All these cases, we have done the algebra enough number of times, and all the algebra is given up there. And all of these guys are going to be ending up with the trivial solution. What's the meaning of a trivial solution? I mean, I've been using this so many times. What is the meaning of a trivial solution? Which means y equal to 0, right? Nothing is going to come out of that, right? Y equal to 0, or those so-called constants are going to come out to be equal to 0. So that's the trivial solution, and you get nothing out of there. So all of these guys, if you are going to do the algebra, which is all given up there and which we have done now n number of times, once again, trivial solution means a solution that is not useful to us. Okay, so if you put y equal to 0, that of course is going to satisfy that equation, but it gives me nothing, right? So that's why it's called the trivial solution. Okay, so if now 1 minus 4 lambda is less than 0, then we are going to be ending up with a situation where I'm going to hope to get some eigenvalues. Okay, so this is the situation, and what is the solution therefore? So y becomes equal to c1 e to the minus x by 2 cosine of 1 minus 4 lambda by 2x plus c2 e to the minus x sine of 1 minus 4 lambda by 2x. Okay. So this is what you mean by a solution with either a damping or otherwise solution. So this is the guy who is going to do your damping, and this is the one that is going to give you your oscillatory component. Okay. So in here now, let us go ahead and put y0 equal to 0. So if I put y0 equal to 0, what am I going to get? If I put y0 equal to 0, what is the solution going to come out as? Pardon me? C1 is 0. Okay, very good. So if I put x equal to 0 here, this guy becomes cos 0 is 1, sine 0 is 0, and therefore since y is equal to 0, C1 is equal to 0. Okay, very good. All right, so we are ending up with y equal to e to the minus x by 2 sine 1 minus 4 lambda x. Okay. Okay, we put the second condition now. Which is y2 is equal to 0. That was my second condition. So this becomes equal to this guy here, and if I put C2 equal to 0, what happens? Again, I'll get the trivial solution. Okay, so I don't want to do that. E to the minus x by 2, x is equal to 2, so this guy is e to the minus 1. E to the minus 1 is not equal to 0. So these two guys are out, and what we get is sine of 1 minus 4 lambda by 2. X is equal to 2, so this is gone. So you are going to get root of 1 minus 4 lambda is equal to n pi. Okay, so this is what I'm going to get by looking at the other condition there. Okay, so this is going to give me what my lambdas are, right? So my lambda is going to be equal to whatever. I'll square these two guys, and then I'm going to get n pi square by 4, and then I take, so I'm going to get plus 1 by 4. Okay, so lambda is going to be equal to that. Okay, so you have lambda is going to be n pi square by 4 plus 1 by 4, and then for different values of lambda I'm going to get my solution. Okay, so this should be 4 lambda minus 1. Okay, okay, so we get my y solution. So far everything is straightforward, whatever we have seen. E to the minus x by 2, that was the whatever was right there, and then you have got sine of 1 minus 4 lambda, and that we have said is n pi by 2, and there is an x. Okay. So this is my solution to that equation. Now we have made a big deal about it by saying that this is in the Sturm-Liouville form, and we want to exploit that now. Okay. So what we say is, what happens to the eigenfunctions when I'm having a Sturm-Liouville form of the system, of the differential equation? The eigenfunctions are orthogonal. Okay. What orthogonality means is just this: f m f m w is equal to 0. That's what orthogonality means. Okay. Now, you don't want to give any physical meaning to that orthogonality or that term orthogonality, but I have got this, which means that I can now express any function in terms of these y's which I have. So any function f is equal to summation of Cn and e to the minus x by 2 sine of n pi x by 2. Okay. Any function here, and these are the eigenfunctions that are orthogonal to each other. Okay. Except at the ends there is going to be trouble that we will see in 1 minute, but otherwise you have got any function f, I can express it in this particular fashion. Okay. What is Cn? How do I get Cn? Who will give me Cn? If I don't get Cn, then do I have anything? I have nothing, right? Even in the Fourier series, we said something about sines and cosines, but we said that we needed these Cn's. How did we get the Cn's? We had sine n pi x by L, we multiplied by that. So in here, we are making a big deal about these guys being orthogonal, right? Orthogonal means what? Orthogonal means that inner product of the two functions with respect to the weight function is equal to 0, right? Let us assume that that is correct. The inner product is 0. Now we get rid of all of this, and we have this. So what should I write for Cn now? Cn is equal to what? Cn is equal to, okay, that's Bn, hardly matters. So Bn, so any function so Bn is going to be equal to what? Integral of P times what now? Why are we making a big deal about this orthogonality? What is so special about orthogonality? What is so special is, if I have got integral of, so I have got integral of e to the minus x by 2 sine n pi x by 2 multiplied by e to the minus x by 2 sine of m pi x by 2 equal to what? Equal to 0. Why? Orthogonal. Okay. This is one function, this is one function. Unless this w is there, this guy is not 0. Okay? Unless that w is there. Remember, that's why we did all that algebra in the first place, to show that this is in the Sturm-Liouville form. Okay? So, to put it in the Sturm-Liouville form, we made sure that that px is equal to e to the x, wx is equal to e to the x. So the orthogonality is only with respect to that weight function. So we need to be careful about that. Okay. So I need to put in this e to the x there. Then and only then they are orthogonal. Otherwise, no. Right? And now you can see the reason why this example was picked is because this guy now goes away. And I know that these functions are indeed orthogonal. Right? I know that. Right? So therefore, that's why we have picked this example, so that it is easy for us to, and every time this may or may not happen. Okay? So it's easy for us to understand that when I'm going to try to look for orthogonality, this indeed is going to end up with orthogonality. Okay? So these functions, e to the minus x by 2 sine n pi x by 2, which were the eigenfunctions, are orthogonal with respect to the weight function, and indeed you can see that they are orthogonal. Okay, so that's what that blue guy there is doing for you. So now you see that 0 to 2, right? 2 is the limit, and remember we always have said that this function was 0 to L n pi x by L, and it was always orthogonal. Okay. So the function which is here, p is equal to this. Now you can go ahead and say Bn is integral of p times e to the minus x by 2 sine n pi x by 2. This is the eigenfunction multiplied with e to the x, which is the weight function, divided by integral of e to the minus x by 2 sine n pi x by 2 the whole square, multiplied with e to the power of x. And in this particular case, the e to the minus x by 2 e to the x cancels out, and indeed you see that the denominator is going to be an orthogonal function. Okay. It's easy to see here that when n is not equal to m, this guy will always cancel off. When n equal to m, it becomes equal to whatever. As of now, that's not important. Right? So in the Fourier series, we had ensured, or the Fourier series ensured, that this guy was equal to unity. That's why this never was there. Okay? That's the only difference between this and the Fourier series, nothing else. Okay? So the orthogonality is exploited in the Sturm-Liouville system, so that once again, just like the Fourier series, you can express any function in terms of this. Okay? There's only one problem in all of this, which is what happens at the endpoints. What's the problem? How what will cancel? Okay. So how is it going to cancel? Okay, that's what we have been saying all along, orthogonality. Okay. So Bn, okay, let's just open this up. This guy is this summation, right? Okay, so this summation is B1 e to the minus x by 2 sine of 1 pi x by 2 plus B2 e to the minus x by 2 sine 2 pi x by 2 plus B3 dot 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 dot. This is equal to P, right? And what is the meaning of orthogonality? If I'm going to multiply both sides with e to the minus x by 2 sine of whatever, 1 pi x by 2, for example. Okay, I multiplied both sides with e to the power of minus x by 2 sine 1 pi x by 2. Multiply this sine 1 pi x by 2. Multiply this with sine 1 pi. What happens to this term when I integrate this? What happens to all these terms? They're all zeros. That was how we obtained the Fourier series also. That's why the orthogonality was important. Okay, so all these guys go to 0, and therefore in a compact form we just say that Bn is going to be equal to int. And this happens only because the governing equation, or the so-called Sturm-Liouville, this guy here, is in that bracket of Sturm-Liouville system, right? The only big problem here is that any function, provided x is greater than 0 and less than 2. Okay? Because at 2, that is going, the function is going to be forced to go to 0, just like when we had in the Fourier series. Okay, so it's going to converge to some number in between, right? So at the end points you may have a small trouble, but otherwise it's going to be perfectly fine. Okay, but that's what we are anyway interested in. Okay, all right, anything else now before we leave this business of Sturm-Liouville system? Basic.
Let me just point out one thing, that any function px that you are expanding right now, that px is not this px.
That no. This sorry.
Just a confusion.
Okay. So this was the way we had written that Sturm-Liouville system. Yeah, I think maybe that's something that you might want to. So I'll just change this notation here, and we'll make this fx like I had nicely written there. So this guy is part of that Sturm-Liouville system, right? And this px is this guy here. Okay, so that is that px. Okay, so there is a notation issue. So this, if I make it f, I think everything will be fine. Okay, so that's a nice point. It's a notational issue. Summation of bn yn, let us call it f of x, because that p is reserved for that Sturm-Liouville system that we were talking about. Okay, so instead of this p, we'll make it into an f. Anything else? Okay, so when I post these, I'll just make that into. Okay, so now let us get back. The main reason why we went into this Sturm-Liouville system was because we were looking at partial differential equations, and there was an ordinary differential equation that came about when we separated the variables, and we ended up in a situation where we did not know how to get these bn's from the summation solution. Okay, so it's very possible. It's very possible. Now there'll be a home assignment where a partial differential equation will end up with that exact same differential equation, and you would have to move down and then get the solution by looking at the fact that that's going to become a Sturm-Liouville system. Okay, all right. So the reason why we went ahead with all of this rubbish is because we wanted to understand how this functions can be evaluated, and therefore the orthogonality came into picture. and therefore we said that the Fourier series also in some sense is going to be emerging from a differential equation which conforms to the Sturm-Liouville periodic system. Okay, so now let's get back to our partial differential equation. So ut is uxx. Okay, so this was the partial differential equation that we have been talking about. And so far, we have always said that the conditions or the boundary conditions were homogeneous. Now we are going to relax that. So u of at x equal to 0 and all time t is now u1. This is the first relaxation that we are giving. The next relaxation is where we are going to make it as a function of time. But as of now, let us just say that this is a constant u1 and u of L and t is going to be u2 and u at all x time t equal to 0 is again some px. Okay. So this guy is our domain and this is the initial condition. Okay. So there's an initial condition and there's a domain and that's that. Okay. Now if you try to go ahead and get the separation of variables sorted out, we'll say that u is going to be equal to f times g. F is a function of t only, g is a function of x only. F is a function of x only, g is a function of t only. Okay. So that's what we have always been doing. Okay. And once you plug that into that, you're going to get something. But the first thing that we also wanted to do was to go ahead and see if I can separate the boundary conditions. The boundary conditions have to be separable also. Okay. So which means that f at x equal to 0 and at all time t is going to be equal to u1. Now, when we had a 0 here, life was easy. Okay. We could just say that f of 0, when this was the case, we said f of 0 equal to 0 and then we just moved ahead. Whereas now, I can't do such things. Okay. So I need to have another strategy before I go ahead and do the separation of variables. Okay. And that is a fairly common strategy. What you say is u is going to be equal to a u homogeneous, which is going to be a function of x and t, plus another function psi, which is going to be a function of x only. Okay. So u is going to be a function of x and t, which is this here. We are hypothesizing that, or we are assuming that that's going to be uh x and t plus psi of x. Okay. On the face of it, it looks like we have done nothing. We have replaced somebody who is x and t with another guy who is x and t and another guy who is x. Okay. But it turns out it gives us a major simplification, which is, now let's just plug this guy in there. Okay. So u of t is of t, and then I have got a psi of x. X is not a function of t, psi x is not a function of t. So this becomes equal to xx plus psi double prime of x. Okay. What we have done is, we have said that we assumed that u was equal to uh plus a psi, And then we said that we plugged this into the governing equation, ut plus uxx, and we just did brute force algebra and we came up with this guy here. So far so good. Okay. Always you need to look at the boundary conditions also. So my u0t is u1, which means of 0t plus psi of 0 is equal to u1. That's one of my conditions. Okay. The other condition is u at L and t is equal to u2. at L and t plus psi at L is equal to u2. Okay. So we have said that UH0T plus psi 0 is equal to this much, and this is equal to this much. Now what do? I have to make life easy for myself, right? Which means that, and I know how to solve this. We have done enough on this now. We know how to solve this. When what happened? When I had U sub H at 0T was equal to 0 and U sub H of LT was equal to 0, and of course that other condition there, right? Now if I look at this, what is the choice that I can make? What is the choice that I can make? I can make a choice which is something which is going to make life easy for me. I'm going to say that I'm going to choose psi 0 equal to u1. If I choose psi 0 equal to u1, then UH0T automatically is equal to 0. I know the solution for this. Similarly, UHLT plus this, I'm going to choose this. Automatically, UH of LT becomes equal to 0. Okay. What about the last condition? UH at x, all x and time t equal to 0 was equal to p of x plus psi of x. What should I do with this condition? I really don't have to make much of a choice. I take this guy to this side. This was px. Px minus psi x is some other qx, right? So I know how to solve this. Okay. So what we have successfully done is to say that, okay, what we have successfully done is to say that I have UH of x and t, UH of t is UHXX, and what happens to this guy here now? It's equal to 0. Great. So I will choose now psi double prime of x equal to 0. And what are my conditions on psi? Psi 0 equal to u1, psi l equal to u2. Do I know how to solve this? Yes, straightforward, right? Straightforward ODE. Psi is equal to ax plus b. And then my boundary conditions are known. So this guy is done. So I know what this guy is, okay? And now I have got this guy here, UHT is UHXX. This is my choice. UH0T is equal to 0, UHLT is equal to 0, and UHX0 is equal to Px minus psi of x. I have already solved for psi of x, right? So I get what is UHX0 as Px minus psi of x, right? So I already know the solution for this guy, and I have pushed in that psi of x for which I obtained the solution, and this guy is another q of x, and I just need to go ahead and use the solution which I already have and obtain the new solution. Same old stuff. Okay. Basically, what have we done? There was a non-homogeneity in the system, and what we have done is to say that by a judicious choice of a variable, we have killed that non-homogeneity, and the system got converted. So just to summarize now, we had a non-homogeneity in the system. We said U is equal to a homogeneous part plus a non-homogeneous part, and then we had UH of t is equal to UH XX, UH of x equal to 0 all time equal to 0, UH x equal to 0 all L equal to 0, and UH at all x and at time t equal to 0 is sum px minus psi x. I know how to solve this, except I don't know what is this psi x. And we have psi x double prime equal to 0, psi of 0 equal to u1, psi of L equal to u2. I use this to solve for my psi of x. So essentially I had a non-homogeneous partial differential equation. We just chose the u equal to a homogeneous part plus a psi of x, and then we just played around, did a little bit of algebra, and then we have used the same old solution that we had in the past to get a solution to this non-homogeneous system. The only problem here being that these guys are constants. We'll relax that. Okay. What happens if, suppose now, let's just take another case where we say u sub t is u sub xx plus, let me say now the non-homogeneity is in the governing equation itself. What happens now? Can I use the same strategy? Can I use the same strategy? Maybe, right? I mean, this is a strategy that you have used here. If it works, great. If it doesn't work, that's fine, right? So what you can do is ut, you say that u once again, and let us say the boundary conditions are the same as in the past. So you hypothesize that u is going to be some UH plus a psi. Okay. So again you are going to get a UH, you are going to get a UH XX, and whatever is this one here plus psi double prime plus phi. So what is it that you are going to choose therefore? I would like to choose this equal to 0. Okay, I'll choose this guy equal to 0 because I know this guy is going to be giving me the same solution, right? I have already solved this fellow here. Okay, and what do I do with my boundary conditions? I do the same thing that I did here, which was UH was equal to 0 for all x time, for x equal to 0 all time, for x equal to L all time, I choose this equal to 0, and UH at all time at time t equal to 0 and x is going to be now equal to, again, whatever was px minus this psi of x, and this is slightly more difficult to get a solution to than what we had in the past. Okay, so I think we'll stop here today. I'll see you again on Thursday. Thank you very much.